Okay, so we're looking at this nice 3D geo proof of Desargue's theorem from this Lemmas in Olympiad geometry book. Yeah. Okay, so we're doing we're doing this proof in two steps. So the first step is what if like Desargue's theorem is a theorem about two triangles on the same plane, right? Okay, but if we're going to expand into 3D, then we should maybe also allow two triangles to be in different planes. So it's like a three-dimensional version. Okay, and so the thing is, if you assume that say you have two different, so A, B, C, and D, E, F are your triangles, okay? And their perspective about a point in the sense that if you join the corresponding vertices, they're concurrent at P, okay? We want to show that if you join the corresponding sides, okay, this is like your X, Y, and Z, okay, that those X, Y, and Z are collinear, all right? But the thing is, if they're not coplanar, okay, then we just have to show that x, y, like it suffices to show that x, y, and z lie on the intersection of the planes of each individual triangle. Because if that's so they first have to exist, and then if they exist, they lie on the intersection of planes. The intersection of planes is a line, right? Okay. Um, or the intersection of planes is empty, or it's the same plane, right? But we just assume it's not the same plane. That's the original starting point, yeah? And then if they're on different planes, we show that they actually don't, they intersect because they intersect at P. Yeah. So the fact that BE, hold on, what is that saying? So the fact that BE and AD intersect at P, right, shows that PADEB, all 5 points are coplanar. Yeah. For those two lines to intersect. Yeah. So of course, two lines might or not intersect if they're in three dimensions, right? So if they're all coplanar, right, then that means AB will intersect DE at Z because AB and D are coplanar. Okay. And it's in the same plane as P, right? But that's maybe not as relevant. It's more that it's in the same plane as the plane of triangle ABC and the triangle DEF, so it's in the intersection. Okay. And that applies to all three, so then it's collinear. All right. So now what do you do if they're not coplanar, right? If they are coplanar. So now we got this diagram and put the everything in the same plane now. Okay? So we denote that plane the purple plane. Yeah? So P is on that plane, X, Y, and Z are all on that plane. Yeah? The two original triangles are on the same plane. Okay, so what do you do? Well, take you take a point G that's not on the plane. Okay? So you're basically trying to disrupt the coplanar condition. So you get the G outside the plane. Okay, now I'm gonna do everything there in black, right? So you define G prime to be any point on GA. Okay? And then you define A prime to be any point on GD. Sorry, not any point on GD, to be the intersection of GD and PG prime. Okay? Okay, so you've kind of artificially set up a situation where you have perspective triangles through P that are not coplanar. Okay? So the triangles in question are actually um, A prime EF together with um, so G prime BC, okay, as it says in the book. But it doesn't say some of the other things, which is like A prime DE together with G prime B. You know what I mean? It's the D prime AB. You know? And it's also um A prime AE not AE, sorry. A prime, what am I talking about? F, DF, yeah? For G prime A, C, yeah? So now these are pairs of perspective triangles, perspective about P, and they're not coplanar. Well, they could be coplanar, but that only happens in degenerate cases that you can kind of tweak around, okay? So let's just assume they're not coplanar, and then um, and then the conclusion of the the non-coplanar Desargue theorem we just showed is that um, so maybe we'll label there's certain things which are of interest. So it's A prime E intersect G prime B. That's of interest, okay? Um, and it's also A prime F intersect G prime C, yeah? Those things are of interest. Let's call these things like S and T, yeah? Okay. So if you apply Desargues to all three, this one gives you that, it gives you that X, S, T is collinear, yeah? Okay. If you apply it to this one gives you G it's obviously A prime D intersects G prime A. That's just the definition of G, right? Okay, so the second one tells you GS and I think it's Y or Z. Z is collinear. And the other one gives you GT Y is collinear. Yeah? Okay, so there's actually like a typo in the book, I guess. So it says project about, what does it say? Project about E, right? But it means project about G, yeah? Okay, so what does it mean for it to be collinear? So X, S, T lie on a line, yeah? And so if we project about, so what are we doing? We take a line, okay? It's kind of this diagram here. So we take a line here. So this is X, this is T, and this is S, right? And we're projecting this line from G onto the purple plane, right? So the projection of a line onto a plane is still a line, right? And we also know that T goes to Y in the projection because GT and Y are collinear, right? And S goes to Z because GS and Z are collinear, right? Okay, and then I guess the crazy thing is now G takes X actually to X because X is on the same plane as Y and Z, right? So it has to fix X, right? Because you're projecting onto the plane. And so therefore now X, Y, and Z are collinear. Okay. Lucas, you get that? This guy. Justin, it's all good. Yeah, that's pretty nice, right? Okay, so I guess Justin has to go now. So we'll try to do the converse for homework, okay? Yeah, Converse. Converse for homework. We can either yeah. So I can either talk about we can either talk about on Tuesday or Saturday. Okay. Any questions? And next Sunday, obviously.